Hello friends. So today we are going to solve the questions from modern physics, and these questions are from year 2024, and we are going to solve 23 questions, and all these 23 questions are from the mains. And for the year 2024, this is part second. We have already solved 27 questions in the part 1 for the year 2024. Topic was the same, that is modern physics. So first question, it states that a hydrogen atom changes its state from 3 to 2 due to recoil. The percentage change in the wavelength of the emitted light is approximately 1 into 10 to the power minus n. The value of n is. So in this case, it states that when there is a change in state from 3 to 1, the percentage change in the wavelength is given to us as 1 into 10 to the power minus n, and we are supposed to find out value of n. So first of all, we are going to find out the photon energy, that will be our, you can say, without recoil. Then we are going to take the recoil that is being asked in the question into the picture, or we can see into the solution. So we are going to write photon energy without recoil. And the transition is from 3 to 2, therefore we can use the standard formula, that E is equal to 13.6 1 upon n2 square minus 1 upon n1 square, and this comes as 13.6, and we have our 2 square minus 3 square. So from here we get that the value of energy, photon energy, is approximately equal to 1.88 electron volt. We can convert this into joules and multiply by 1.6 into 10 to the power minus 19, which gives us 3.025 into 10 to the power minus 19 joules. Now let us consider the recoil energy of hydrogen atom. Recoil energy of hydrogen atom. And we can use, we can say, conservation momentum, and which states that specifically for this particular question, that the hydrogen atom will recoil with a kinetic energy, suppose that is k, and ultimately this shift in the energy will reduce the energy available to the photon. So it basically means that by conservation of momentum, the hydrogen atom will recoil with a kinetic energy. Let us suppose we denote that kinetic energy as Kr, and because of this distribution of energy will reduce the energy available to the photon. And we can easily find out this kinetic energy, or we can also call it as a recoil energy. You can say our recoil energy, that is our Kr, will be equal to momentum square divided by 2 times mass m. And here P is the momentum and m is the mass. So momentum, we can write our energy upon c and its whole square divided by 2 times m, which can be further written as E square divided by 2mc square. And we know all the values. Energy we calculated, mass is our 1.6 into 10 to the minus 27, c is the speed of light. So we plug in the values, we get the recoil energy will be equal to, we have this as 3.025 into 10 to the power minus 19 whole square, 2 into mass is our 1.6, 10 to the power minus 27, and c is the speed of light and its whole square. So we get the kinetic energy or recoil energy is approximately equal to 3.177 into 10 to the power minus 28 joules. Okay. Now, like I said, there will be fractional decrease in the energy that will be available to the photon. Now we can find out what will be this fractional energy loss. So you can say fractional energy loss and that fractional energy loss, let us call this as delta E upon E. Delta E is our, we can write this as delta E upon E, or we can write this as our Kr upon E, which gives us Kr is our 3.177 10 to the power minus 28. Energy we found out is our 3.025 10 to the power minus 19, and this comes close to as 1.05 into 10 to the power minus 9. And in terms of wavelength, we can write that, or we can say that this is fractional energy loss. This is fractional energy loss, and we also know that our delta lambda upon lambda will be equal to delta E upon E. So therefore, percentage change in wavelength, which was initially asked in the question, so from here we can write percentage change in wavelength will be equal to delta lambda upon lambda multiplied by 100. And we substitute the value, we get this will be equal to 1.05 into 10 to the power minus 9 multiplied by 100, which can be approximately equal to 1.05 into 10 to the power minus 7. And this percentage is given to us as 1 into 10 to the power minus 7. So this we can say this 1.05 is approximately equal to 1. Therefore, it is given as n, not 7, but it is given as n. So if you make 1:1 comparison, we can write that value of n is equal to 7. The value of n is 7. Next question. It states that according to Bohr's theory, the moment of momentum of an electron revolving in fourth orbit of hydrogen atom is. So here we are going to find out moment of momentum, which is nothing but our angular momentum. So this moment of momentum term is also our angular momentum. And for nth orbit, we already know the standard formula. So we can say angular momentum for nth orbit, that is our L of n is equal to n multiplied by h upon 2 pi. Here h is our Planck's constant, n is our principal quantum number, and we are given that it is in the fourth orbit. Therefore, we can write that for fourth orbit, value of n is equal to 4. So accordingly, we can write this as L of 4 is equal to 4 multiplied by h upon 2 pi, and this 4 goes by 2, so we get our L of 4 is equal to 2h upon pi. So this is our angular momentum, or as in the question it asks as a moment of momentum. So we have our answer, option number 3 is correct. Next question. It states that an electron rotates in a circle around a nucleus having a positive charge Ze. Correct relation between the total energy E of electron to its potential energy U is. So in this case, the electron is orbiting a nucleus, and we have to find out the relation between total energy as well as the potential energy. So in this case, we are going to use the basic concept of electrostatic as well as the Bohr model of the atom. So in this particular case, we are going to use our electrostatic and Bohr's model and we know that our potential energy, or we can also call it as a electrostatic potential energy. Okay. So we say that potential energy of the electron and this potential energy will be our due to electrostatic attraction. Due to electrostatic attraction. So that's why sometimes we also call this as electrostatic potential energy. And that is our standard formula. So we can say our U is equal to minus k z e square upon r, where k is our k is equal to 1 upon 4 pi epsilon naught and r is the radius. R is the radius, and it is also, you can say, rotating. So therefore we can write that kinetic energy of the electron will be equal to our k is equal to half m v square, and this will be equal to our negative of the total energy. So it comes as positive k z e square upon half mv square. So yeah, so we can write this as 2 multiplied by r. So therefore the total energy that is our E will be equal to kinetic energy plus electrostatic potential energy. Become this as k z e square upon 2r minus k z e square upon r. So from here we solve it, we get our E is equal to minus k z e square upon 2r, and from here we can write that if we segregate or remove this 2 as about 1 by 2, so this entire will be our electrostatic energy, electrostatic potential energy. Therefore we can write our E is equal to U upon 2, and from here we can write our U is equal to twice E. So U is equal to twice E. Option 4 is correct. Okay. Next question. It states that the angular momentum of an electron in an orbit of radius r of a hydrogen atom is directly proportional to. So this is quite straightforward based on the formula itself. Okay. So here we can just use our formula of angular momentum. Angular momentum of electron that is, suppose our L is equal to our n multiplied by h quantized, or we can write this as our n h upon 2 pi. Here n is our Planck's constant, sorry, n is our principal quantum number and h is our Planck's constant. And now from the Bohr's model, we can write that radius of nth orbit is directly proportional to square of our principal quantum number. And we can just rearrange it, and let us call this as equation number 1 and this as equation number 2. So we can say from equation 1 and 2, from equation 1 and 2, we can write that our n is directly proportional to square root of r, and which can be further written as that our L is directly proportional to n is directly proportional to square root of r. So therefore our option number 4 is correct. Four is correct. Next question. It states that the shortest wavelength of the spectral lines in the Lyman series of hydrogen spectrum is 915 angstrom. The longest wavelength of the spectral lines in the Balmer series will be. Okay. So we are going to start with our Rydberg constant, and we have to remember that in the question it is given that there is a shortest wavelength for our Lyman series. So it means the value of our n1 will be equal to 1 and value of n2 will be equal to infinity. And that will be resulting in shortest wavelength in our Lyman series. And for Balmer series, it states that there should be a longest wavelength. So therefore, value of n will be equal to 2 and the value of n1 will be equal to 2 and value of n2 will be equal to 3. That will be giving us longest wavelength in Balmer series. Okay, so this we have to remember. So first is given as Lyman series. So for Lyman series, our n1 is equal to 1 and it should transition to n2, which is equal to infinity, and this will result in the shortest wavelength. And secondly, we are given Balmer series. So for our Balmer series, n1 will be equal to 2. It transitions to n2, which is equal to 3. And this will be giving us longest wavelength. Now we can use the Rydberg formula for both Lyman as well as Balmer to get the correct answer. So first of all, we start with our Lyman series, and we are given that the wavelength for our Lyman series, let us call this as LS, it is given as 915 angstrom, And from our Rydberg formula we can write wavelength for luminance series will be equal to our RH 1 square minus infinity square. And from here we can find out value of our RH, and we can say our RH will be equal to 1 upon lambda s ls, and this comes as 1 upon 915 into 10 to the power minus 8. This comes as approximately equal to 1.093 into 10 to the power 7 per centimeters. Now Rydberg formula for longest wavelength. So this was for, let me write here, this was for our Lyman series. Lyman series. Now we are going to solve for our Balmer series. And Balmer series, let us call that our wavelength is lambda bs, that is a Balmer series, is equal to our RH. It starts with 2 and end at 3. And this will be giving us RH, and we are going to have 5 upon 36, and we are supposed to find out the wavelength. Therefore we can say our lambda bs will be equal to, this will be 1 upon RH, so it comes as 5 times RH and divided by 636. This will be equal to 36 5 1.093 into 10 to the power 7, and this comes approximately as 6585 angstrom. And for Balmer we have to remember this is our longest wavelength. Longest wavelength. So answer is our 6585. Next question. It states that the ratio of the shortest wavelength of the Balmer series to the shortest wavelength of the Lyman series for the hydrogen atom is. So same question, but in case here it is being asked as our ratio. And for Lyman series it is asking for the shortest wavelength. Therefore we can write that for our Lyman series we want shortest wavelength, and the shortest wavelength will be given as n11 transition to n2 infinity. And we can use our Rydberg formula for our Lyman series, 1 upon lambda ls. Ls is our Lyman series. We have our RH, and 1 upon 1 square minus 1 upon infinity square. This gives us our RH, or we can say 1 upon, and this can be written as our lambda ls is equal to 1 upon RH. Now same we are going to do for the Balmer series. for Balmer series we want both are having shortest wavelength. Yes, so Balmer series also is having our shortest wavelength. Shortest wavelength. So in this case our n1 will be equal to 2 and it transitions to n2, which will be our infinity. Therefore the wavelength 1 upon lambda bs is equal to our RH 1 upon 2 square minus 1 upon infinity square, giving us RH by 4, and wavelength lambda bs is equal to 4 by RH, and we have to find out the ratio. So ratio is for Balmer to Lehman. So we can write that our ratio is equal to Balmer series to Lehman series. Balmer is our 4 upon RH, Lehman is our RH. 1 upon RH, sorry. 1 upon RH, which can be written as 4 upon RH multiplied by our RH. RH and RH cancels out. So this comes as 4 upon 1, or we can say the ratio will be our 4:1. So option 1 is correct. One is correct. Next question. It states that radius of a certain orbit of a hydrogen atom is 8.48 angstrom. If energy of the electron in this orbit is E upon x, then x is given that A naught is 0.529 angstrom and E is the energy in the ground state. So A naught is nothing but our Bohr radius, and E is the energy in the ground state, which we know is given as minus 13.6 electron volt. So we can say that our A naught is our Bohr radius. And value is given to us as 0.529 angstrom, and E is the energy in the ground state. E is the ground state energy. Ground state energy, which is our minus 13.6 electron volt. And we have to find out what will be the value of x. So we are going to start with our Bohr radius formula. So we know that our Bohr's radius formula, that is for nth orbit, our R of n is equal to our A naught n square, and from here we can say, or rather write, that our n square is equal to R upon A naught, and this R is given, it said for a certain orbit, that R is our 8.48 and divided by A naught, which is about 0.529, so which approximately comes as 16. Therefore we can say value of n is equal to 4. Now we can easily use our Bohr energy formula because we found out value of n. So Bohr's energy formula for nth orbit, we know that energy E of n is equal to minus 13.6 upon n square, or we can write this given as our E upon x. Sorry, one second. We can write this as our E upon n square, or we can also write it as minus 13.6 upon n square, which is given to us as E upon x. Therefore, we can say that our E upon x is equal to E upon n square, or we can say that our x is equal to n square, giving us our x is equal to 16. So value of x is our 16. Next question. It states that the longest wavelength associated with Paschen series is, given that RH is 1.097 into 10 to the power 7 SI units. So we have to find out for Paschen series, and the Paschen series, the transition should be from n1 is equal to 3, should be 2 n1 is equal to 3 from a higher level, that is n2, which should be greater than 3. Okay? And we are supposed to find out the longest wavelength. So we can say that for Paschen series, the transition is 2 n1 is equal to 3 from higher level which is our n2, and this n2 should be greater than 3. Okay, for any value greater than 3, that is 4, 5, 6 and so on. But in this case we have to find out the longest wavelength, and for longest wavelength, which means that there should be a smallest energy difference between the two levels, and that is only possible if the value of n2 is equal to 4. So we can say that for longest wavelength, the energy difference, or rather we can say longest wavelength corresponds to the smallest energy difference which occurs for the transition for the transition from N2 is equal to 4 to N1 is equal to 3. This will be resulting in the smallest energy difference, or we can say longest wavelength. Now we can easily use our Rydberg formula. Therefore we can say 1 upon lambda is equal to our RH 1 upon 3 square minus 1 upon 4 square, and this gives us R of H is equal to 7 upon 144, and RH is given to us and we are supposed to find out the wavelength. Therefore we can say lambda is equal to, we have this as one second. Yeah, so lambda will be equal to 144 and 7 multiplied by RH, which is 1.097 into 10 raised to the power 7. So this gives us lambda is approximately equal to 1875 nanometers. Okay, or in terms of option number 4 is correct. It is written in meters, so we can just reformulate it. Lambda is equal to 1.875 into 10 raised to the power minus 6 meters. Okay, so option 4 is correct. Is correct. Next question. It states that in Frank Hertz experiment, the first dip in the current voltage graph for the hydrogen is observed at 10.2 volt. The wavelength of the light emitted by the hydrogen atom when excited to the first excitation level is dash nanometer, and we are given Hc as well as value of E. And here the important term which is mentioned in the question is our first dip. So we have to remember that the first dip in the current voltage graph, it corresponds to first excitation energy of the atom. Therefore we can say our first dip in the current voltage graph corresponds to first excitation energy. It means the first excitation energy is given to us as 10.2 volt, and therefore we can say our first excitation energy, that is our E, is given to us as 10.2 electron volt, and we can use our photon energy wavelength relationship, that is going to give us answer directly. So we can say photon energy wavelength which tells us that our E is equal to Hc upon lambda. So from here we can say our lambda is equal to hc upon E. hc is given to us as 1245 and energy is our 10.2. This gives us 122.06 nanometers. So we get this as 122.06 nanometers. Next question. It states that in a alpha particle scattering experiment, distance of the closest approach for the alpha particle is 4.5 into 10 to the minus 14 meter. If the target nucleus has the atomic number 80, then the maximum velocity of the alpha particle is dash into 10 to the power minus 5, 10 to the power 5 meter per second. So we have to find out what will be this, fill in the blanks. So here, this is just, you can say, relation between the conservation of energy. So we can say conservation of energy, and we have to remember that it is talking about the distance of the closest approach. So which basically means that suppose this is a nucleus and we have charged particle, we have here is alpha particle which is traveling, and it should be, you can say, dead center with respect to the nucleus, and this is the distance of the closest approach. And suppose it is moving with the velocity v, so its kinetic energy just before the distance of closest approach is suppose our half mv square, and at this closest approach it is going to give us a electrostatic potential energy. Okay. So we can use just the conservation of energy. Therefore we can write our half m v square is equal to, we have our k ze upon r, and all the values are known to us. We simply substitute the values and we get this as our, or we can write, let me write in terms of velocity. So we can say velocity square will be equal to, this comes as k multiplied by 2 ze upon mass into radius, and radius is given to us, that is closed approach. So this is our r, and at this particular point the entire energy will be our electrostatic potential energy. Okay. And we substitute the values, we get this our v square is equal to, and k we know is our 1 upon 4 pi epsilon naught, which is our 9 into 10 to the power 9 multiplied by 2, z is given to us as 80, and this comes as our mass ze, and charge is our 1.6 into 10 to the power minus 19 and divided by 6.72 into 10 to the power minus 27, and this is our 80. One second. Twice z, 6.2, and this comes as twice 80, 1.6, something is missing here. So I missed here two things. First I missed my this square, and second I missed this about 2. So this comes my 4 and this about my e square. Okay, now it is correct. I wrote the formula wrong, and this comes as our whole square. I think now it's correct. Okay, therefore we get this will be equal to our 4 multiplied by 9 multiplied by 80 multiplied by 1.6, and this is our 6.72. I missed radius, sorry. Yeah, radius is 4.5 into 10 raised power minus 14, and it also comes as 4.5 into 10 raised power minus 14, and we are left with 10 raised power 9, and this is our 10 raised power minus 19 into 10 raised power minus 19. Okay, so this comes as our and it is our 10 raised power minus 27. And if we solve this, it will be coming as close to our V naught square will be equal to 243.8 into 10 raised power 12, or we are given that V naught is equal to 15.6 into 10 raised power 6, and 10 raised power 5. Okay, so we can write this as our V naught is equal to 156 into 10 raised power 5 meter per second. So if you compare with the given, which says dash into 10 raised power 5, so our value of dash will be equal to 156. So we get this value over 156. Next question. It states that A hydrogen atom in ground state is given energy of 10.2 electron volt. How many spectral lines will be emitted due to transition of the electrons? So we given that initially it is in a ground state, that value of n is equal to 1, and energy given to it is our 10.2. So based on this we are going to find out what will be the possible transition. So we can say that our hydrogen atom is at ground state. It means value of our n is equal to 1, and it should be transitioning to a higher energy, a higher state when energy is given to us. And we can just solve it directly also, because it is given that energy required to excite electron from n1 to n2, this energy is exactly equal to 10.2 electron volt. Therefore, the final state to which the electron will be transitioned is n is equal to 2. So therefore, from here we can say there will be only one spectral lines that is possible. Okay. And we can use the formula also. We can say our number of spectral lines is equal to n into n minus 1 divided by 2. So this gives us 2 minus 1 divided by 2 and is equal to 1. So option 4 is correct. Next question. It states that if frequency of EM wave is 60 megahertz and it travels in air along z direction, then the corresponding electric and magnetic field vectors will be mutually perpendicular to each other, and the wavelength of the wave in meter is. So we are given, frequency is given, and we know that the electric and magnetic field vectors are perpendicular to each other. So this we can just use our standard formula. We need not discuss anything. We are given the frequency, and we know that our wavelength is equal to c upon our frequency. C is the speed of light. So this gives us 3 into 10 to the power 8. Frequency is our 60 megahertz, and this comes as our 5 meters. So option 3 is correct. Next question. It states that a plane wave EM wave propagating in x direction is described by E of y 200 volt per meter sine of 1.5 into 10 to the power t minus 0.05x. The intensity of the wave is. So this is directly based on the formula itself. We know that intensity is equal to half c epsilon naught multiplied by E naught square. So we can write that intensity of EM wave if represented as I will be equal to 1/2 c epsilon naught and E naught square. Here E naught is the amplitude, and which is given as 200. Okay. we substitute the values, rest of the things are standard. So we get our I is equal to 1/2, C is our 3 into 10 to the power 8, epsilon naught is given to us as 8.85, 10 to the power minus 12, and E naught is our 200 and its square. So we get from here that our intensity will be approximately equal to 53.124 watt per meter square. So option number 2 is correct. Two is correct. Next question. It states that an object is placed in a medium of refractive index 3. An EM wave of intensity 6 into 10 to the power 8 watt per meter square falls normally on the object. It is absorbed completely. The radiation pressure on the object would be. So in this case, we are going to find out the radiation pressure, and we have to remember there is 100% absorption. Okay. And we know that the standard formula of our complete absorption radiation pressure that is our P is given as I upon V, and in case there is a complete reflection, then it simply comes as 2I upon V. Let me write it here. It's not asked here, but if there is 100% reflection, then we can say P is equal to our 2I upon V, and V is the speed of light in the medium, and we can easily find out of V. So we can say V is equal to C upon our refractive index, and we have to remember V is the speed of the light in medium. V is speed of light in medium. Therefore, we can say V is equal to C upon our refractive index. C is our 3 into 10 to the power 8. Refractive index is given as 3. So 3 goes by 3. So we get velocity is equal to 10 to the power 8 meter per second. So intensity is given. We can easily find out our radiation pressure. That is, the pressure is equal to I is given to us as 6 into 10 to the power 8 divided by velocity, that is 10 to the power 8. Here 8 and 8 cancels out, so we get 6 Newton per meter square. So option 3 is correct. Is correct. Next question. It states that a plane EM wave of frequency 35 MHz travel in a free space along x direction at a particular point in the space and a time E is 9.6 J unit vector volt per meter. The value of magnetic field at this point is. So we are given wave is traveling in x direction, and at particular point our value of electric field is given as 9.6 J unit vector. It means the direction of our electric field is our in y direction. So we know the relationship between our magnetic field and electric field. So we can say that our relation between electric field and magnetic field in free space, and that is our B is equal to our E upon C, and electric field is given to us as 9.6. C is our speed of light, that is 10 to the power 8. So this comes as our 3.2 into 10 to the power minus 8 Tesla. And now we have to find out the direction. And for direction, we are given that our electric field is in J unit, is given as J unit, and we know that our magnetic field will be perpendicular to both electric field as well as direction of propagation, and the direction of propagation is given to us as in x direction. So we can say direction of wave propagation is our x direction, or we can say simply as a I unit vector. And we know that our electric field is perpendicular to the magnetic field and is also perpendicular to our direction of propagation, which is our here is our I unit vector. All these three are perpendicular with each other. And in order to find out, we can simply write that our magnetic field unit vector will be equal to our unit vector v, that is our velocity vector in x direction, and cross product of our E unit vector. So we have this as our I cross j, this is giving us k. Therefore we can write that our magnetic field will be equal to magnitude 3 into 10 to the power minus 8, and we have this as k unit vector Tesla. So this becomes as our option 1 is correct. One is correct. Next question. It states that the electric field of an EM wave in free space is represented as E is equal to E naught cos of omega t minus kz I unit vector. The corresponding magnetic induction vector will be. So from the given equation, we can see that our electric field oscillates along x-axis and the wave propagates along our z-axis. So we can use the given equation, which is our electric field is equal to E naught. E naught is a magnitude cos of omega t minus kz I unit vector. Therefore from here we can say that our electric field oscillates along x-axis, which is basically our I unit vector, and we can also say that our wave propagates along z-axis. And we are supposed to find out, first of all, let's find out direction. Magnitude is quite easy to find out because magnitude relationship is just our along with c. Okay, speed of light comes into the picture. And let's find out first of all the direction of magnetic field. Direction of our magnetic field, and we know that for EM wave our electric field is perpendicular to magnetic field is perpendicular to direction of propagation. Direction of propagation. All these three are perpendicular to each other. And with respect to our wave vector, which is our k vector, points along plus z unit, and we know that our electric field is along I unit. Okay. Therefore, we can say that our, based on these two combination, we can use our right hand rule and find out that our magnetic field B is our along y unit vector, or we can also call it a j unit vector. Okay. In the question it is mentioned that j, so let me write it j unit vector. And magnitude is quite easy. We can say that our magnitude that is our B naught will be equal to E naught divided by c, where c is the speed of light. Therefore, we can write that our magnetic field B will be equal to our, this is magnitude B naught cos of omega t minus kz, and direction is our j unit vector, or in terms of E naught, we can write this will be equal to our E naught upon c cos of omega t minus kz j unit vector. So we get this as E upon c minus option number 2 is correct. Option 2 is correct. Next question. It states that in a plane EM wave, the electric field oscillates sinusoidally at a frequency of 5 into 10 to the power 10 Hz and amplitude of 50 volt per meter. The total average energy density of the EM field of the wave use epsilon naught as 8.85 into 10 to the power minus 12 our Coulomb square per Newton meter square. And in this case, it is a little bit tricky because the actual formula which gives us that the average density of EM wave is the combination of, because of electric field as well as the magnetic field. So let me first of all write that formula. So we can say our average energy density of EM wave it is given as u, which will be equal to our half epsilon naught e square plus half b naught square upon mu naught. And so we also know that in case of EM wave, both electric as well as magnetic field contributes equally towards the energy density. Okay. So this part is important, because if we go into the formula, it looks like that energy density should be the energy because of the electric field plus energy because of the magnetic field. But there is another technical, you can say, term that is associated with this our energy density, and which is that for our EM wave, the electric field and magnetic field contributes equally to the energy density. So the contribution of our electric field and magnetic field towards energy density is equal. Okay. So therefore, we are only going to find out the energy density only because of one part, that can be because of electric field as well as because of a magnetic field, and that will be same. Okay. So in this case, it is talking about our electric field, so let's deal with the electric field. Therefore, we can write that therefore we solve only one part, and that one part can be either electric field or it can be magnetic field, to find total energy density. So therefore, we can say that our total energy density, that is our U, will be equal to energy density because of electric field, which will be equal to our half epsilon naught E square. And we are given all these values, so we can just plug in them. Epsilon naught is given as 8.8, 5 into 10 to the power minus 12. Electric field is given as our 50, and this comes as whole square. Therefore, we get that our total energy density will be equal to 1.10625 into 10 to the power minus 8 joules per meter square. If we use both, so it means because of first part, it will be also our 1.1, and because of the second part, it will be also 1.1. So it will be coming as 2.2, which will be wrong option. Okay, 2.2, and this zeros can just vary. So the correct option will be our option number 1. Okay, so neither third or fourth is correct. So we can say option 1 is correct. Next question. It states that the electric field of in an EM wave is given by E I unit vector 40 cos omega multiplied by T minus Z upon C Newton per coulomb. The magnetic field induction of this wave is. So we are given the standard equation, and let me first of all write the equation. So we are given that electric field is equal to 40 cos of 40 cos of omega t minus z upon c, and this is whole multiplied by I unit vector. In standard notation we normally write like this. Here only difference is this I unit vector is put in the first. Okay. So from here we can at least see that our electric field is along our I unit direction, that is our x direction. So we can say that our electric field is along x-axis because of this I unit vector, and the wave, EM wave, will be traveling along positive z direction. Or we can say that our EM wave travels along positive z direction. So first of all we are going to find out the direction, because finding out the magnitude is quite easy, that is just based on the direct formula. So we can say that our direction of our magnetic field will be equal to our, this is our k unit vector cross our E, and our electric field is in our I direction. So let me put it, that is our k unit vector cross I unit vector, which gives us our j unit vector, and so direction is our j, and magnitude that is our b naught will be equal to E naught upon c, and E naught is our 40, so this comes 40 upon c. Therefore we can write that our magnetic field B is our B naught cos of omega t minus z upon c, and direction is our j unit vector. B naught is our 40 upon c, so we can write this is our 40 upon c, and j is put along, let us put it here, j cos of omega t minus z upon c. So therefore option number is our J40. Option 4 is correct. Next question. It states that an alternating voltage of amplitude 40 volt and frequency 4 kHz is applied directly across a capacitor 12 microfarad. The maximum displacement current between the plates of the capacitor is nearly. So this is directly based on the formula. We know that the maximum current, or we can say displacement current, that is I max, will be equal to omega c times v naught. And or we can also write it as 2 pi f c times v naught. We substitute the values, we get this as 2 pi, frequency is given to us as 4 into 10 to the power 3, capacitor is given to us as 12 into 10 to the power minus 6, and v naught is given to us as 40. And this will be giving us that Imax is approximately equal to 12. So option 4 is correct. Correct. Next question. It states that EM wave traveling in a medium with a speed of 1.5 into 10 to the power 8 meter square, the relative permeability of the medium is 2. The relative permittivity will be. So this is also based on Directon formula. We know that the ratio of speed of light in air or vacuum divided by velocity of speed of light in a medium is equal to square root of the product of relative permeability as well as relative permittivity. So we can know that our C upon V is equal to square root of our mu r and our epsilon r. So from here we can say our mu r epsilon r is equal to C upon V whole square, and relative permeability is given to us as 2, or let us write it as mu r epsilon r is equal to C is given as 3 into 10 to the power 8, and velocity in the medium is 1.5 into 10 to the power 8 whole square, and this will be coming as 2 because this 10 8 cancels out. This will be 30 divided by 15 will be giving us 2 square, which is equal to 4. And from here we can write that our E of r is equal to 4 upon mu of r, which is given as 2. So this 4 goes by 2, giving us that our E of r, which is our relative permittivity, is equal to 2. So option number 4 is correct. Is correct. Next question. It states that in the given EM wave, EY is 600 sine omega t minus kx volt per meter, the intensity of associated light beam is in watt per meter square, given that epsilon naught is 9 into 10 to the power minus 12. So this is directly based on the formula. We know that intensity of a EM wave is given as 1 by 2 C epsilon naught E naught square. So we can see intensity of EM wave, if that is represented as I, then this I will be equal to half C epsilon naught and E naught square, and E naught is given to us in the question, that is our 600, and rest of the values we already know. So we substitute it, is comes as half into 3 into 10 to the power 8, epsilon is given to us 9 into 10 to the power minus 12, and this is our 600 whole square. And we get that our I will be equal to 486 watt per meter square. So option 1 is correct. One is correct. Next question. It states that a plane EM wave is propagating along x direction. It has a wavelength of 4 mm. If electric field is in y direction with the maximum magnitude of 60 volt per meter, the equation of the magnetic field is. So this is, you can say, directly based on the formula, except we have to find out here two things. First, we are going to find out the frequency, and second, we are going to find out the wave vector. And magnetic field relationship with electric field is quite simple, we already know it. So first of all, let's find out our frequency. We can say our frequency f will be equal to c upon wavelength, that is our lambda, which is given to us. So we can write this as c is our 3 into 10 to the power 8 and lambda is given to us as 4 millimeter. So this comes as 4 into 10 to the power minus 3. This gives us that our frequency is equal to 75 into 10 to the power 9 hertz. And we can convert easily into angular frequency, and which is our 2 pi f. And let's find out our wave vector. Wave vector, which is represented as k and is equal to our 2 pi upon lambda. So this comes as about 2 pi upon lambda is about 4 into 10 to the power minus 3. This gives us pi by 2 into 10 to the power 3 per meter. And we already know the relationship between electric and magnetic field. So we know that our magnetic field B is equal to our electric field divided by C. Magnetic field is, electric field is given to us 80, C is into 3 into 10 to the power 8 meter per second. So 60, sorry, not 80. So this comes as 2 into 10 to the power minus 7 Tesla. And we know that our electric field, magnetic field and direction of propagation are always perpendicular to each other. So we know that our electric field is perpendicular to our magnetic field is perpendicular to our direction of propagation. So from, at least from the given option, one thing is for sure is that we are going to have, okay, we have to find out omega. So let me find out omega. So which can be found out from here. Omega will be equal to over 2 pi f, which will be equal to pi multiplied by 2 pi, and that will be coming as, or this will be our let me write it 2 pi f. We can just solve it out later on because how it fits in the equation. Okay, it's not a big problem. So at least from all the given options, we can at least see that the relationship between our this will be multiplied by our wave vector and this will be our omega. Okay, and everywhere there is a presence of our negative sign. All the options are giving us a negative sign. So from here we can make a rough approximation that the wave equation, or we can say the wave is going to propagate in x direction and the oscillation will be perpendicular to the both x direction as well as electric field. Okay, so which basically is a z direction. If we say that based on the given equation that we are having this electric field in y direction. So we can say that one second. Okay, there is only one option, that is our option number 3, which is giving this as a I unit vector. Okay, and rest all 3 are is with respect to our k unit vector. But here there is a difference in the magnitude. So at least we can just segregate which of the option will be the correct one. Okay, and so our magnitude of our magnetic field is 2 into 10 to the power minus 7. So at least option 3 and option 1 is incorrect. So at least we can say I unit vector will not be the direction. Okay. So only correct option is will be either our 2 or it will be 4, and it will be giving us a k unit vector. Okay, so from here we can make a rough approximation for that. And it is also given in the question that our electric field is in y direction. Okay. So if electric field is in y direction, then we can write that our magnetic field, that is our B, will be equal to our B naught sine of kx minus omega t, and with this has a k unit vector. And now we simply substitute the values. B naught is our 2 into 10 to the power minus 7, and this is sine of, and our k vector is our pi upon 2 into 10 to the power 3, and we can write this as pi into 2 into 10 to the power 3 multiplied by x minus this is our 2 pi, and f is our 75 into 10 to the power 9. One second. Yeah, 75 or 15. So therefore, according to the given equations, we can just modify it, and this can be written as our 2 into 10 to the power minus 7 sine of, and this is our pi by 2 is our common, so we can take pi by 2 as common, and there is only x, so we have to take, so option number, obviously B will be correct one, because x is our multiply by here as 1, so therefore we can write pi into 10 to the power 3, and we have this x, this will be equal to minus 3 into 10 to the power 8, and this is multiplied by t, and this is our k unit vector. So the option number 2 will be the correct one. Option 2 is correct. Next question. It states that the magnetic field in a plane EM wave is given as By 3.5 into 10 to the power minus 7 sine of 1.5 into 10 to the power 3 x plus 0.5 into 10 to the power 11 t Tesla. The corresponding electric field is this. So this is quite inverse of the, first of all, let's find out the magnitude. So we know that our E naught, let me write here magnitude. So we have our E naught is equal to C times B naught, and B naught is our 3.5 into 10 to the power minus 7. So we get this as 3 into 10 to the power 8 multiplied by 3.5 into 10 to the power minus 7. So we get our E naught is equal to this will be 105 volt per meter. From here also we can make that option 2 should be correct. Okay, but anyways, we can just find out the direction also. Direction, and magnetic field is so we know that our B vector is our y direction, or we can also say it as a j unit vector, and our wave vector which is our k, and this is in the formation of k multiplied by x. So we can say from kx implies propagation along minus x axis. Therefore, we can write that our A cross B will be giving us k unit vector. Therefore, we can write that our electric field will be equal to x comma t will be equal to 105 sine of 1.5 into 10 to the power 3x plus 0.5 into 10 to the power 11 t, and this is our k unit vector. So option number this is A of z, so which basically means it is going to have a k unit vector. Okay, and similarly it is given as B of y, so it will be associated with a j unit vector. Okay, so option 2 is correct. And one second, so here this x, it is, let me write in a standard form, otherwise this x basically means the direction of the propagation. Okay, so therefore let me write it as E of z, otherwise it will be a problem. So this k unit vector is our direction of this z. This is the last one. So this completes all the 23 questions from the year 2019 for the year, sorry, not 2019 but 2024, and this was the part 2 for the year 2024. So this completes all the 23 questions for the year 2024 mains part 2. Thank you.